So this is the example of the Twitch solution. So you could see table 4.5 here from our textbook, the viscous fluid flow. So this is actually the prediction of Twitch and a few scientists here. So so this is the velocity profile that proposed by certain people, a few people. So and then Twitch will use this kind of equation, all of these actually, and then it proposed the x mean the distance where the separation occurs. So this is the numbers or the value proposed by the Twitch, and this error is actually based on the value of x here proposed by Blasius. Actually, it's because it say we have the exact solution here. Okay, so as I said, it's not easy to do on a paper. Okay, so and then okay, let's say we are now trying to evaluate the velocity profile of 1 minus x squared. So this is might be not totally similar with what we learned previously in u over u over u, y per delta, and so on and so forth. So this is actually based on the real application. So and then to simplify our calculation, I hope you could do u by the power of 5 and then use terms of 1 minus x squared. So and then you will have this equation. Okay, so another ideas about what is actually this velocity profile. So it is actually the stream function. Okay, so as you know, stream function is actually psi, and psi is actually reflect the flow rate. So sometimes they use that idea of ideal flow to propose the velocity, because if you look back into the velocity profile that proposed by the von Karman, so we have a u over u here. So this is actually the ratio between the local velocity and the free stream velocity. But in this equation, okay, in this velocity equation, it is actually depends on the value of x. So it is actually a graph showing you the flow line for that certain situation. Okay, just to make sure that you have idea of this one. Okay, for example, we start with the common velocity profile, so which is u is equal 1 minus x squared. So and then so we have a u by the power of 5 here in this terms. Okay, so you need to multiply it 5 times, so you will get this one. So and then we need to start with this equation. So this is the general step. So we need to solve this equation, and then finally we need to draw a graph actually. So we need to determine what is the value of lambda. We assume that separation occur at minus 0.09. So and then we need to find what is the value of x. So this is actually the whole work for Twitch solution. Okay, next. Okay, let's say we start to solve the momentum thickness equation. So we have theta square here. So this is the equation, and then we substitute the value. So this is the trick. So it is okay for us not to substitute the value of u by the power of 6 here. First, we need to do the integral part. So we substitute the value of u by the power of 5. So we have here. So and then we need to integrate it with dx, and then we substitute with the limit of 0 to x. So now we have this term. So and then to reduce it, to simplify our calculation, we assume that all of this term is actually equal with one integral. So for example, we assume that it is equal to a. So and then from this equation, okay, So we could simplify it as 0.45 nu A over U by the power of 6. So nu here is actually the kinematic viscosity. Okay, so but it is okay not to substitute with the value of kinematic viscosity, because we could cancel it later on. So now please understand know that now the long terms like this one, so it can be simply simplified as this one. So I think you could neglect about this term. So I just typo of this one. So and then we substitute the value of theta square. So that's why in certain textbook they will give you, so they bring you the nu here to the left hand side. So they straight away I could get the square theta square over nu, so it's equal to 0.45 A over U 6 here. So for example, we have here, so and then we replace the value of theta square over nu here with what we have. So if you could see here, so we substitute the 1, and then we will get 0.45 nu A over U by the power of 6 and nu. And nu here can be cancelled actually. So and then we need to solve the problem of this one, dx of 1 minus x squared. So this is actually come from the idea of du dx. So we know that u is 1 minus x squared. So we differentiate it, du dx, so we get it's minus 2x. So and then we could solve this problem. Lambda is equal to, so lambda is equal to 0.9 minus 0.9x A over U6. So and then what you need to do is you need to expand the value of A. So we substitute with the value of A here. So and then the equation will become like this. So and then because we have another x here, so to simplify our calculation, so we merge it with the another x term, so and then we get this equation. So and then this equation, so we need to calculate what is the value if lambda is equal 0. What is the value of x that makes lambda is equal negative 0.09. So we found that x is equal to 0.268. So means that if we have our object here might be an aerofoil and so on and so forth. So and then it's the separation occur at x equal, for example, this is an x-axis, so it's equal occur at x 0.268 meter. So this is the separation start to occur. So this is the imagination of this answer. So this how to do this is actually you need to use your Excel at least, or you could if you could solve it by using MATLAB and so on and so forth, so you are allowed to do that. So I just show you the simple one. So we use Excel, so we have the value of x here, and then we have the value of lambda. Okay, and then if we plot a graph, so we could get a graph like this one. So and then the lambda value is negative 0.09 here, so it actually occur at almost 0.26 something. So that is the idea. So that's why because this is the idea to conduct research about this one, and then if you search in Google about Thwaites method, Falkner-Scan method, you will find that there are no okay, let's say there are no simple notes about this one. So they will come with a research paper. So research paper means a journal paper telling you how people try to enhance this equation and so on and so forth. Because another reason is the separation is actually not only depends on velocity. As I said, it's depend on the it depends on the surface condition. That's why in certain technology, so they will use a surface, they will use the idea of artificial surface roughness to create separation, because it will give it will influence the lift force and also the drag force of our object. So, and then I would like to share another thing. So, a Twix method for asymmetric flow. So, this is what I talked previously, because we have a planar surface and also we have the asymmetric flow. So, the asymmetric flow is when we deal with the circular motion, the circular object. So, this is the side view. Okay, so let's say we have something curved like this, like a bullet. So if the boundary layer occur at this surface, so we found that if we see from the front view, so that's, let's say this is the front view. So we found that the boundary layer will occur like this around the object. So, and then you could cut at any plane. If you want to cut at X plane here, or you could cut at here, okay, you will see same you will have same boundary layer image. Okay, that is the basic idea of asymmetric flow. So in terms, we could say that a flow pattern is said to be asymmetric when it is identical in every plane that passes through a certain straight line. The straight line in question is referred to as the asymmetric axis. So and then from the in terms of the axis, so in asymmetric flow we usually use the polar coordinate. So the terms of radius usually comes out in asymmetric flow. So again, so the asymmetric flow for Twix is actually has a little bit modification, and it's done by Rod Crabtree names, a person named Rod Crabtree. So sometimes you will find it is also known as Rod Crabtree method. It was written in our textbooks, okay? But it is okay for you to imagine that this is actually the Twix equation for the asymmetric flow. So we have two basic equations, so which is the momentum thickness theta square here, and also the value of lambda. So the only difference is the value of r square being added in the equation. So we have the r square, r naught square here. So and then we still have the value of lambda, is still the same, and the limit of the separation is negative 0.09. So there are no different in terms of limit, and there are no different in terms of the value of lambda. And the r naught here is actually the maximum radius. So the radius of our object. Okay, let's say we have a free stream velocity flow past a sphere. Okay, so let's say we have this one. So I think you are familiar with this term. So we have the u square, and we have u equal 1.5 u naught sine x over a. So I think if you refer back to our ideal flow, so we have some kind of the x component, or maybe the y component, the r components or the theta components of flow around cylinder is showing something like this one. So we have sine, we have cos, and so on and so forth. So and then here, so we have r naught is equal the a sine x over a. So a is actually the sphere radius, and x is the stagnation point. So this is actually showing that if we have a sphere here, and then if we have flow here, so we have the stagnation point at this one. So and then we have an a as sphere radius. Okay. So and then we could have the value of r naught here. Okay, let's say this is the theta. Okay, so the idea is actually come from this one. So and then the u naught here is the inlet velocity of stream. Okay, so we do the same things. Okay, so I think you get idea. So for example, we have du dx in terms of lambda. So let's say we have du dx is actually the differential of 1.5 u naught sine x over a, and then we get this term. So and then this is the theta square. So we have the r naught square here. So and then nu is still the kinematic viscosity of the flowing fluid. So what we need to do is the might be the biggest challenge here is we need to multiply the value of u 5 times. So because we have the u by the power of 5 here. Okay, so and then we substitute everything. So in this calculation, let's say we bring the theta square over nu to the left hand side. So we have this term. So we substitute the value of u by the power of 6 of this one. And then this is the value of r naught square. So and then this is the value of r square, r naught square, and this is the value of u by the power of 5. And then I think you have no worries about this one because this term is quite simple because we don't have any plus minus. So it's different with 1 minus x previously, because when we have plus minus sign, so the term will become longer. So and then we do all the solve this equation. So we could find that it will give us like this one. Okay, so and then okay, so and then we determine the lambda. So we have the lambda here. So and then we okay, so we have the value of lambda d theta square. I'm sorry. Oh well, we still not integrate this one, I think. Okay, so we do it here. So we have lambda d theta over nu, theta square over nu. So we have all these terms. So and then we multiply with du d theta. So this is the du d theta that we calculated previously, and then the lambda will become like this one. So and then we do the integral of sine x over a by the power of 7. So we will have these all terms. Okay. So and then to simplify this one, because we have x over a here, so we simplify x over a here as x here. So and then we could have lambda 0.13 cos theta x and so on and so forth, or something like this one. So again, okay, you need to solve this by using at least Excel to help you to solve this one. And then, for example, we just substitute the value of x in terms of angle. So and then we could get the value of lambda. And then finally, we could get the minus 0.09. Lambda occur at 103.6 degree. So it means that if we have a sphere here, okay, let's say this is the 0 degree, so this is 90, so the separation is occur at this point. So the flow will flow around it, and then the flow will flow on the surface and then at this point they start to separate. Okay, that is actually the assumption of this calculation. So this is the graph. Okay, so we'll have this one. So and then means that you need ability to try to evaluate your equation with graph, because sometimes you could see the whole situation by looking the trend of the graph. Okay, so that is about the tweets. So and then another phenomenon that occur when you have a separation and so on. So another phenomenon is called the wick. So wick is actually when the flow goes into the empty area, empty space, and then it will create chaos. That's the idea. Okay, awake is the defect in stream velocity behind an immersed body in a flow. A slender plain body with zero lift, such as the aerofoil parallel to the strip, usually produce a smooth wake whose velocity defect U1 decays monotonically downstream. So it will the velocity defect here occur at the back of the object. Okay, but there is research to estimate at what situation the defect velocity will occur. So, and then some of them say it is between around 3 times the length of our object. So this is the idea. So here, we are going to show you, we are going to solve this by equation, because we are not going to solve to derive the equation. But again, for the laminar wake here, okay, we still have two types of equation, because it is depend on the axis of the situation. So for this aerofoil, okay, for sure wake is actually occur when we have a pressure gradient. So when we have separation and then the wake occurs, so means that it's occur at a curved surface. However, for aerofoil like this one, okay, so as I said, it is not asymmetric flow. So because it is can be determined as 2D laminar flow. So for this one, okay, so this is the example of wake and so on and so forth. So my separation is start occur here. So and then so they will have the imbalance of the velocity at the back, because usually if we illustrate this velocity according to the idea of ideal flow, we could say that, okay, the velocity will back to normal at the end here. So here the velocity is actually the same as the incoming velocity, free stream velocity here, because it should be back to normal. But in reality, because of viscous effect, the viscosity take part, it create separation. The pressure is different, so the separation occur, and then the wake start to occur. Okay, so we come back to the idea of force is equal CD times 1 over 2 rho AU square. So, and then we could calculate CD here, and then we need to calculate the velocity defect of U1 here. So by using the idea of this one. Okay, so where the U1 here is the defect velocity, the U naught here is actually the free stream velocity, and the nu here is the kinematic viscosity of fluid. Okay, so this is the example. For example, air at 20 degrees Celsius at 1 atm flows 1 meter per second plus a slender two-dimensional body. So it's quite and something like an aerofoil, a length of 30 centimeters, whose drag coefficient is 0.05 based on plane area BL. So I think you could imagine it is referred to we have something like this one. So we have a flow here, and we base on the area of this one, area of B and L. So the width actually is B, and the length here is the L. So assuming laminar flow at 0.3 meter downstream of the trailing edge, estimate the maximum wake velocity, 1% wake thickness, and the wake thickness Reynolds number. So at 20 degrees Celsius, so the rho is 1.205, and the mu is 1.81 times 10 by the power of minus 5. So, and then the body length Reynolds number, so means that we need to know the Reynolds number that occur on our object here. So we take the L here is our dimensional parameter. So we use the idea of rho UL over mu. So we substitute the value, so we could get it is around to 20,000. So for x equal to 3, So means from the center line of here. So the length, this one, okay, is actually 0.3 meters. But you could imagine that if we have an object here, so we, okay, on x-axis here, so might be here is 3 meters. Okay, the center line where defect velocity is computed by applying the equation that we have. So we have this one. So, and then if we substitute all the value, we know the CD, Reynolds number, and so on and so forth. So, and then we could find that the U here, so it's equal to 0.315 meter per second. So, and then the wake half thickness could be defined as the point where the defect velocity drops 1% of its maximum velocity. So from the idea of Gaussian profile, so we use this equation, we equal it into 0.01, and then we substitute, we means here is y at 1%, 0.01. So, and then we could get that y is 0.0288 meters, and the half weight of half thickness, so we divide into 2, so the width is actually 0.0288 meters. So this is the assumption of actually the length, the size of the wake that occur on that situation. So, and then the wake Reynolds number can be calculated like this: rho, U, and B. So B is actually the width that we have here. So, and then we could get it is around 604 value. Okay, so we continue a little bit. So, for example, when we want to discuss another type of wake which occur at symmetrical flow, okay, so we need to use another equation. So the equation is a little bit different at these terms, okay, because it doesn't have any Reynolds number. I think, okay, we have a Reynolds number here, but this is for planar, so still in x and y axis. So, but in asymmetrical, so we have this equation. So I hope you could imagine, remember this one. But now we are open book test 1, test 2, and also final. So I think I hope you could bookmark this one. So this way is actually occur at if we have a sphere or something like that. So we imagine that it can be a wake like this, and this is the experimental evidence. So this is at Mach number 1.53. So, and this is the Mach number 4.01. Okay, so it is incompressible flow actually, but I just like to show you the evidence of wake. So, and then this is the idea. So let's say we have the idea is still the same. So we have a 20 degrees Celsius, 1 ATM flow, 1 meter per second, and a slender body of revolution. So it means that it's just some kind of a revolve body. So it means it's something like a sphere. So its length is 15 centimeters, whose drag coefficient is given here as 0.008, and assuming L square. So might be this is the idea of this is a sphere, and we have the L here times 2L. Okay. So it's assumed that it might be a slender body like this one, I think. Okay, we take the, okay. So, and then assuming laminar flow at 0.3 meters, so downstream of the trailing edge, as we estimate the maximum wake velocity defect and 1% wake thickness, and also the wake thickness Reynolds number. So, and then this is the data, and this is the equation that we have. So we don't have any Reynolds number, so we have this one, and then we substitute everything. So we could get the U max is 15.9 centimeter per second. So and then we could calculate the R equal to 1%. Okay, so we don't have any X here, so we have R here. So we could get it is around 0.0288 meters, and we could calculate the weight thickness as 5.76 centimeters. So and then we could calculate the Reynolds number as 610.